Most of us learn that there are three states of matter: solid, liquid, gas. And maybe if your teacher was feeling generous, they added a fourth: plasma. But plasma is not just another phase, it's a whole different behavior of matter: wild, charged, and alive with motion. And once you see how many forms it can take, you'll start to realize plasma isn't one thing, it's many. It can be searing hot or strangely cold, chaotic or exquisitely structured. It can swirl in the upper atmosphere, flash through the sky, or perhaps be recorded on your phone as a beautiful orb. And yet, for all of its appearances, we don't talk about it enough. Well, maybe except for on this channel. But either way, today we are going to be exploring the different modes plasma has. Because once you start to see what plasma can do, you'll never think of space or matter the same way again. When most people hear the word plasma, they picture something blazing, something on fire, and they're not entirely wrong. Hot plasmas are the most familiar, but perhaps not the most extreme, as you will see. These hot plasmas occur where temperatures are so high that electrons are ripped from atoms, creating a soup of charged particles. The result is electrically conductive, magnetically active, and incredibly dynamic. We can see this kind of plasma right here on Earth. Every lightning bolt is a natural plasma discharge, heating the air to over 30,000 Kelvin, hotter than the surface of most stars. In that moment, atoms are torn apart, and what's left is a glowing filament of plasma that crackles through the sky. This form of hot plasma comes not from nature, but from human ambition. Inside magnetic fusion-like reactors, such as tokamaks and stellarators, scientists are trying to recreate the conditions needed for nuclear fusion. They use powerful magnetic fields to confine plasma in toroidal or twisted shapes, pushing temperatures into the hundreds of millions of degrees. That's hotter than the core of a star. At these temperatures, fusion becomes possible, but only if the plasma can be kept stable. That's not easy. Hot plasmas are notoriously unruly. They wiggle, twist, and generate instabilities, little ripples that can erupt into full-blown disruptions if not contained. That's why researchers spend years studying plasma confinement, turbulence, and something called magnetic reconnection, a process where twisted field lines snap and rejoin, releasing bursts of energy. But not all hot plasmas are the same. Some are magnetized, dominated by the motion of their own self-generated magnetic fields. Others are relativistic, with particles moving so close to the speed of light that their mass effectively increases. And even in labs, we've learned to shape plasma into tools. We have plasma mirrors which reflect ultra-short laser pulses with atomic precision. And don't forget about plasma Wakefield accelerators, where beams of light ride with the ripple of a plasma wave, effectively accelerating particles without the need for miles of magnets. These high-temperature plasmas are not just a scientific curiosity. They're the frontier of energy, propulsion, and the deepest questions about how matter behaves when pushed to its limits. But for all their power, hot plasmas are only one part of the story, because there's another kind, something more subtle, structured, and sometimes cold. Some of the most fascinating forms of plasma are cold plasmas. In physics, it can also be called a non-thermal plasma, and it is one in which the electrons are energetic, but the heavier ions and neutral particles remain near room temperature. This imbalance allows cold plasmas to exist without destroying the material around them. Cold plasmas are typically generated by applying an electric field to a gas at low pressure, often in a sealed chamber. The field accelerates electrons without significantly heating the entire gas. These energetic electrons ionize atoms and molecules in short bursts, creating a dynamic yet cool plasma state that can be sustained with radio frequency, microwave, or pulsed power inputs. The precise mix of pressure, power, and gas type determines the plasma's behavior. But cold plasmas aren't just something we make in labs. They also form naturally in Earth's upper atmosphere, in the ionosphere of planets, and in the vast, low-density regions of interstellar space. In these environments, sunlight or cosmic radiation can ionize particles without generating much heat, resulting in extended regions of cold, diffuse plasma. Even the outer layers of comets, where the solar wind interacts with escaping gases, this can form cold plasmas that trail into space. These natural examples are key to understanding how plasma behaves across the universe, not just in stars, but in the quiet spaces between them. One thing that is super interesting is that cold plasma is now being used in medicine to disinfect wounds, promote tissue healing, and even kill certain types of cancer cells, all without heat or chemicals. It's also being explored in agriculture to help seeds germinate faster, and in environmental tech to break down pollutants like nitrogen oxides or volatile organic compounds. But the real mystery begins when you look at its structure. Under the right conditions, cold plasmas can self-organize, forming double layers, plasma crystals, or long filaments of charge. In experiments with dusty plasmas, where the plasma contains tiny charged particles like microbeads or cosmic dust, researchers have observed self-assembling helical structures, vortices, and cell-like enclosures. Some of these configurations even exhibit feedback loops, memory-like behavior, or reaction diffusion patterns like those that shape biological forms. And when these dusty plasmas are studied in microgravity on the International Space Station, for example, these plasma crystals form a complex, lattice-like structure that's been seen to move, divide, and sometimes behave in some eerie ways. And this isn't metaphor. These are real, measurable behaviors emergent from physics. Plasma is responding to electric and magnetic fields, boundary conditions, and charge differentials. But the outcome is something that looks patterned, coordinated, and sometimes astonishingly alive. So while cold plasmas might lack the raw energy of fusion, they offer something else: structure, pattern, and maybe even a hint of self-organization that takes plasma to the next level. And all of this together, in my opinion, changes what most of us think plasma is capable of. Some plasmas are so extreme, so unusual, that they don't fit neatly into any categories at all. These are the exotic plasmas, plasma states that stretch the limits of temperature, density, and theory. And while a few of these overlap with hot plasma, we're returning to them here because they profoundly diverge from classical behavior and thus fall in this category. One example is quark gluon plasma, a state of matter that existed just microseconds after the Big Bang. In this phase, protons and neutrons break apart into their constituent quarks and gluons, forming a dense, hot soup that flows almost entirely without resistance. This isn't theoretical. It's been created in particle accelerators like the Large Hadron Collider, where heavy ions are smashed together at near light speeds. Then there are pair plasmas, composed entirely of matter-antimatter pairs, like electrons and positrons. Here, because both particles have the same mass, the usual asymmetries of regular plasma don't apply. Pair plasmas are thought to occur in pulsars and black hole jets, where the conditions are so intense that matter and antimatter form and annihilate in constant flux. We also see relativistic plasmas again in this group, but here we're going to touch on their deeper theoretical significance. These are plasmas in which the particles move close to the speed of light. Their mass increases, their magnetic fields intensify, and they begin to obey relativistic rather than classical physics. Relativistic plasma show up in the astrophysical jets and gamma ray bursts, where space and time themselves seem to wrap under the pressure. There are also theorized states like magnetized quantum plasmas, where quantum effects, strong magnetic fields, and high-density interactions all converge. These are especially relevant for modeling the behavior of white dwarfs, neutron star crusts, and some next-generation fusion systems. In such environments, particles become strongly coupled, meaning their interactions can be treated independently. Quantum states begin to dominate, and the plasma behaves more like a collective quantum fluid than a classical gas. And then there's speculation around dark plasma, analogs to ordinary plasma, composed of hypothetical dark matter particles. While still theoretical, dark plasmas are proposed in some models to explain cosmic structure formation and may someday help us understand how the invisible scaffolding of the universe is shaped. These exotic plasmas are rare. Some are only found in high-energy physics labs or extreme cosmic environments, but they remind us just how broad the plasma family really is. It's not just a phase of matter, it's a spectrum of behaviors that reveal themselves only when the universe is pushed to its limits. Some plasmas behave so unpredictably, so strangely, that scientists have struggled to model them. These are what some researchers refer to unofficially as wild plasmas. They are not defined by temperature or density alone. They are defined by complexity, by emergence, by behavior that seems to break the rules. Wild plasmas can form in natural settings where electric and magnetic fields interact chaotically. They can be found in earthquake zones, thunder clouds, or even around volcanic eruptions. In these environments, shifting geologic pressures can generate piezoelectric currents or rupture underground rock layers, creating localized electric fields that ionize nearby gases. The result? Floating balls of light, pulsing strands, or self-contained glowing orbs that defy easy classification. Ball lightning is one of the most famous examples, described as glowing spheres that hover or drift, sometimes even passing through windows. Ball lightning remains one of the least understood plasma phenomena. Despite eyewitness reports, including those from this channel, high-speed footage, and a handful of lab-created analogs, Its exact formation mechanism is still debated. And let's not forget about the upper atmosphere, where other wild plasma forms appear during thunderstorms. We have sprites, blue jets, and elves, all large-scale luminous events that burst upward from storm clouds into the stratosphere or ionosphere. These are electrical discharges, essentially transient plasma structures, triggered by lightning but shaped by complex electric field interactions above the storm. They were once thought to be mythical, but are now confirmed by satellites and high-speed cameras. Now let's turn to one famous ground-based example, which comes from Norway's Hesdalen Valley, where low-altitude luminous orbs have been documented for decades. Some researchers suggest these may be plasma phenomena triggered by underground minerals interacting with atmospheric conditions, ultimately creating a natural plasma discharge system. Others have proposed that these strange sightings involve dusty plasmas with feedback loops capable of sustaining their structure far longer than expected. In labs too, wild plasmas emerge. In high-energy discharge experiments, researchers have observed self-contained plasma blobs, also called plasmoids, that rotate, oscillate, and even appear to resist diffusion. Some configurations seem to stabilize using double layers of electric charge, effectively forming a kind of membrane around the plasma itself. These structures can persist far longer than theory predicts and occasionally exhibit unexpected responses to nearby fields. And while the physics behind these behaviors is still unfolding, and I'm here for all of it, the implications are profound. If plasmas can self-organize, store energy, or even respond to their environment, then perhaps the boundary between matter and behavior isn't as fixed as we once thought. Wild plasmas remind us that not everything in nature is simple, linear, or predictable. Some of it pulses, some of it twists, some of it behaves more like weather or biology than basic ionized gas. But most often, it does something that really makes us wonder, what are we seeing? Speaking of seeing, what did we just see in this video? We explored the hot plasmas of fusion, lightning, and astrophysical jets. We uncovered cold and structured plasmas with their strange ability to self-organize into crystals, filaments, even cell-like enclosures. We traveled through the world of exotic plasmas, quark gluon soup to pair plasmas to dark and magnetized states that challenge the edges of known physics. And then we ended with the wild plasmas, the kind that flicker in the upper atmosphere, roam fault lines, or even flash like intelligence in the dark. Each of these is more than a phase of matter, in my opinion. They seem like behaviors based on physics, emergent, responsive, sometimes rule-breaking. And it reminds us that plasma is still the most misunderstood state in the universe. If this kind of science speaks to you, then this channel is for you. I have made many videos about plasma, and I don't plan on stopping anytime soon. In closing, plasma isn't just out there in the stars. It's woven into our technologies, our skies, and often our thoughts.